Hello and welcome to the second in the two-part series looking at Floyd's algorithm, which is on the second year of the Decision 1 content for the Further Maths A-Level. In this video we're going to be looking at an example implementing Floyd's algorithm and then looking at an idea of how it might be used in an exam. So this is the example we're going to look at. You can see just off my whiteboard there I've got the instructions that we looked at in the previous video. I'll move the whiteboard around so we can see those sort of broadly at the same time. This is the example we're going to be looking at though. Use Floyd's algorithm to produce a table of shortest distances and routes for the network shown below. Okay, so you can see here we've got 4 vertices. So we've got a 4x4 grid. Now, as I said in the previous video, this grid is typically given to you and quite often it'll look like this. If it's not given to you, you do need to be able to draw it out yourself, but I think that's highly unlikely. So you can see here we've got basically identical grids. Side by side. On the left, we're going to be looking at the distance tables, and on the right, we'll be looking at the route tables. So let's have a look back at the instructions. So we need to make both the initial distance table for the network and the initial route table. We're only looking at direct connections. Whoops. Okay, so that's what we're going to be doing here. Now, personally, I like to title my tables while I'm working. Because I think it helps me keep track of what I'm doing. So we've got our initial tables. So we know that, well, we can see there's no loops. So the distances from A to A is nothing. We don't worry about it. So we can see the distance from A to B is 8, or weights. A to C is 6. And A to D, there isn't a direct route. So we put an infinity sign in there. B to A is also 8. B to C is 5. And B to D is 6, and so on. Being careful here, C to A is 2, and so on. So C to D, there is no direct connection, so again we put an infinity sign. D to A, no direct connection. D to B is 6, and no direct connection to C. So this is the initial distance table. Now, we didn't go through how to fill out a route table in the previous videos, so we're going to look at that now, and it's very, very straightforward. All you do is you take the top letter of the label of the column and fill that in all the way down. Like so. So what this table tells us is currently the distance to get from A to B, so from A to B, goes through B, which is to be expected. And that distance is 8. That's what this kind of tells us at the moment. When we finish the algorithm, we'll look at how to use this table to find some routes. So that's the initial setup. So what we're going to do now is we're going to do iteration 1. So the first thing first is we copy the first row and column from this distance table into our matrix. So again, I would like to label first iteration, and the letter I'm considering is A. You don't need to do this, but again, I feel it helps me keep track. So we copy the A row and column. We don't copy here. We'll come back to this later. So what we then do is we shade in. Now, you shade in lightly so it can still be read. That's very difficult for me to do using a digital whiteboard, so I'm going to shade in a different color. So we shade that in. So what we're going to look at is we're going to go, okay, these are still effectively 0. So we look at this box. We've got this C box here. Currently, the distance to get from B to C is 5. If we go B to A and then to C, the distance is 8 plus 6, which is 14. So 14 is bigger than 5, so we write down the 5. And we keep going. 8 plus infinity is definitely bigger than 6. 2 plus 8 is bigger than 5, so we write the 5 down. Likewise there. And then infinity plus 6 is the same size as infinity. Now, we've noticed here, after the first iteration, nothing changes. That's okay, sometimes it won't. Because nothing's changed here, this root table will also be the same. So we fill that in. And that's the first iteration done. As I said, just because stuff doesn't change, that doesn't mean you've done it wrong. Sometimes it doesn't. Remember, what we're doing is saying, okay, we're now going to see if any of the paths to get from this vertex to this vertex are shorter going through A than going direct. And it turns out that they're not. We then repeat the process for each vertex. So for our second iteration, we're going to be looking at B. So we copy the B row and column into our new matrix. And then again, we shade that in. Now don't forget, with the shading, your numbers still need to be visible. So make sure you're not colouring it in darkly. Okay, so let's go through that process again. 8 plus 5 is 13. That's bigger than 6, so we write the 6 down. Now we can see some stuff's going to change. Because 8 plus 6 is 14. That's definitely smaller than infinity. So what we do is we write 14 in square brackets. Now the square brackets are not compulsory, but what this does is it identifies to the examiner, I have changed this number. Because that's what the examiner is looking for, and it makes it much easier for them to mark if they can see, oh, I've changed it. We've now changed a number here, which means we need to change an entry in our root table. Because what this tells us is the route from A to D that goes through B is length 14. And that is shorter than going from A to D directly. So what we'll do is we replace the entry in the root table with a B. And again, we'll put square brackets around it. And we keep going. Okay, so that's 2. Oops, I didn't fill that in. So we can see 5 plus 6 is less than infinity, because it's 11. So again, we're going to put a B in there. And we'll keep going. Eight plus 6 is 14. We put a B in here. Be careful with this. Once you start filling in this table, it becomes very easy to look at the wrong numbers and go, 2 plus 6 is 8. That's small. We're looking at the ones that you've shaded, so be careful with that. And again, 6 plus 5 is 11. What we now do is we now copy the entries from our first iteration root table into our second, not replacing the ones that we've changed. So everything else is going to stay the same. And that's the second iteration done. What this means is that the route from A to D goes through B. Okay, and at the moment, we can go, okay, we're going from A to D, so it's A to B, so we'll look at B, and then to get from B to D, you go to D. So it's currently, the route is A, B, D. And the same thing's true of these other entries we've changed. So we're going to continue, and we're going to repeat the process for the third iteration and then the fourth. They will give you at least enough tables that you need, probably more in case you make a mistake. Now, when we copy down the numbers for our third iteration, we take out the square brackets. So you can see for our C column, we're going to have 6, 5, dash, and then 11 without the square brackets. And again, 2, 5, 11 without the square brackets. So what I'd like you to do is pause the video and have a go at doing the third iteration now. And this is what you should end up with. You can see that we've changed only 2 routes. So what this is saying now is the route to get from B to A, the shortest route so far goes through C. Notice how we didn't change anything over here with the B's, or from the B's, so I've taken out the square brackets because nothing changed. Likewise here with the 14 and the 11s, nothing changed, so I've not put them in square brackets. The fourth and final iteration is doing the same process with D, so I'd like you to do that now. And here's the answer. So this is the last iteration because, again, we have 4 vertices, so we're going to be doing 4 iterations. Again, like our first iteration, nothing changed, so nothing's in square brackets. This is the answer to this part A of this Floyd's algorithm question. What we're going to look at now is how to use this table to answer further questions. So this is the example we're going to look at. Find the shortest route from D to A. So I'm going to do some annotations in red on what you're doing on our final graph here, but you don't need to do these annotations in an exam. You just write down the route. You might have to justify it, so that's why we're going to go through an explanation. We can see that the shortest distance from D to A is 13. Okay, that is the shortest distance from D to A, but we need to figure out what that route is. So we're going from D to A. So where we start with is, okay, we're going to go from D to A. We can see that we are needing to go through C. So our route is going to become DCA. So what we then do is we then check D to C and C to A. So D to C goes through B. C to A doesn't go through anything else. C to A ends up at A. So what this tells us is that D to C goes through B, C to A stays as it is. So our shortest route from D to A is DBCA. And the length of the route is 13, because we can see it's 13 there. And that's how you use this table, is you look at what sort of intersections there are. And that's really it for Floyd's algorithm. As I said, it's very unlikely that you're going to need to do this for more than 4 or 5 vertices. I don't think I've ever seen it for 5 from the textbook or in the few papers that we've seen. But I don't think it's something I don't think they would do, but they could in theory. but more likely it's going to be 4 because, as you can see, it's quite a long algorithm, even if it is quite straightforward. Now, things that students tend to forget are the shading. The shading's really important. It tells the examiner that you are looking at this particular vertex. That's important. If the question says explain why the shortest route from D to A is this, well, you would explain that the route table says going from D to A, the entry in DA is C, which means that it goes through C. D to C goes through B. C to A doesn't, so the route is then D, B, C, A. And you'd write that in words. Floyd's algorithm, as I said, is one of those algorithms that's not particularly difficult, but just takes a long time to do. So that's why quite often they will give you this grid in the exam, so you don't have to spend time writing out 10 matrices, because that is a lot. So you can see here, just zoom out a little bit further, everything for Floyd's algorithm. And that's it. That's Floyd's algorithm. The Graphs and Networks chapter, and the Algorithms on Graphs chapter, and the Chinese Postman chapter that we'll look at in some future videos, the second year content is only one thing in addition to what you've already done. There are some later chapters or later topics where it's a massive extension on what you've done in the first year, or it's something that's entirely new. So those topics will require more videos, but we'll get to them as we get to them. But otherwise, that's Floyd's algorithm, and thank you for watching.